So we're now going to apply the addition formulas to come up with the so-called double angle formulae, which are essentially formulas for sine 2 theta, cos 2 theta, and tan 2 theta. So we want formulas for these in terms of sine theta, cos theta for these two, and for tan theta here. So let's just illustrate for cos 2 theta. So this is the same as cos theta plus theta, and then recall from the formula book, cos A plus B is cos A cos B minus sine A sine B. And so this is cos squared theta minus sine squared theta. And there are a couple of different ways we could rewrite this. So cos 2 theta equals this is the first important thing. But we can also rewrite this, observing that sine squared theta is 1 minus cos squared theta, and that just comes from sine squared plus cos squared equals 1. So this is also the same as cos squared minus 1 minus cos squared, which is 2 cos squared theta minus 1. And then the other way we can write this is we could instead replace the cos squared with 1 minus sine squared. And we could write it purely in terms of sine squared. So the cos squared becomes 1 minus sine squared. The other sine squared we leave alone. And we get 1 minus 2 sine squared theta. So there are 3 different formulas for cos 2 theta. The double angle formulas, none of them are in the formula book. But you can work them out by using the cos A plus B, sine A plus B, tan A plus B formulas, which are in the formula book, and just letting A equal B. But these 3 formulas for cos 2 theta are important. My suggestion would be to learn them because you will need them all. And we'll also see, for example, later when we do integration, these 2 formulas here are important, but this one is also useful. So really all 3 are useful for you to know, and I recommend learning them. Now on to sine 2 theta then. Sine 2 theta again is sine theta plus theta, which is sine theta cos theta plus cos theta sine theta, which is 2 sine theta cos theta. Again, this second line just comes from the sine A plus B formula, where A and B are both theta. So again, this formula here is another one that it helps to recall quickly, so you might like to learn it. But if you forget it, you can always very quickly work it out from the sine A plus B formula. And then lastly, tan. We're going to do the same thing. Tan 2 theta is tan theta plus theta. And then recall tan A plus B is tan A plus tan B over 1 minus tan A tan B. So we get on the top 2 tan theta over 1 minus tan squared theta. And then okay, so those are the 3 double angle formulas. And what I want to, so question, can we find a formula for sine 3 theta in terms of sine theta and cos theta? And the answer is obviously yes. The details for that one I'll leave to you. The one I want to look at, and you can do the same for cos 3 theta. It's a good exercise. I think there's one like that on the homework, I think. Let's do tan 3 theta. Tan 3 theta is tan 2 theta plus theta, which is tan 2 theta plus tan theta over 1 minus tan 2 theta tan theta. And then tan 2 theta we just worked out is 2 tan theta over 1 minus tan squared theta. Okay, and then let's multiply the top and bottom of the big fraction by 1 minus tan squared theta. So this first thing becomes just 2 tan theta. The next thing becomes tan theta times 1 minus tan squared theta. The 1 we multiply by 1 minus tan squared theta. And then here at the end we have 2 tan theta times tan theta, which is 2 tan squared theta. And then if we expand everything out and simplify, we've got 2 tan theta plus tan theta, that's 3 tan theta, minus tan cubed theta over 1 minus tan squared theta, minus 3 tan squared theta. Now, why have I written it like that, where it doesn't quite line up? That was intentional. So let's just add a number 1 in here. My question is, what's special about these numbers 1, 3, 3, 1? And indeed, going back to this, what's special about these numbers 1, 2, 1 here? Do they remind you of anything? Maybe not yet. So let's just, for fun, I can't see this being asked in the exam because it's a bit too much in terms of doing algebra, but let's just do tan 4 theta. So this is tan 3 theta plus theta, which is tan 3 theta plus tan theta over 1 minus tan 3 theta tan theta. And then let's just use our previous answer. That's 3 tan theta minus tan cubed theta over 1 minus 3 tan squared theta plus tan theta all over 1 minus 3 tan theta minus tan cubed theta over 1 minus 3 tan squared theta times tan theta. And let's multiply everything in the top and bottom by 1 minus 3 tan squared theta. So we will get 3 tan theta minus tan cubed theta plus tan theta times 1 minus 3 tan squared theta all over 1 minus 3 tan squared theta. That's what the 1 becomes. And then minus 3 tan theta minus tan cubed theta times this tan theta that's at the end. Now let's tidy up. So on the top, notice we've got here 4 tan theta. And then we've got minus 4 tan cubed theta. And then in the denominator, we've got 1 minus 6 tan squared theta. And then plus tan to the 4 theta. And then notice that's a 1 there. So the numbers we've got are 1, 4, 6, 4, 1. Have you spotted the pattern yet? 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. We've seen this before. This is Pascal's triangle. So this is an absolutely wonderful relationship that I discovered earlier this year. When I say I discovered it, I mean I discovered it for myself. I'm sure many people have discovered it before me. But yeah, in general, it can be proved, and I have proved, that tan n theta is given by n choose 1 tan theta minus n choose 3 tan cubed theta plus n choose 5 tan to the 5 theta and so on over 1 minus n choose 2 tan squared theta plus n choose 4 tan to the 4 theta and so on. Proof of this is a bit beyond us for now, but yeah, that's really interesting, really unexpected. Yeah, it's you wouldn't expect to come across Pascal's triangle in this context. So I think, yeah, that's a very surprising relationship. Okay, so now what can you be asked? So you could, this tan 3 theta question, you could be asked to express tan 3 theta in terms of tan theta in the exam. That, I think, would be a reasonable question. Tan to the 4 theta is probably too much work. But anyway, on to kind of other examples that you could have to do. So let's say given x equals 3 sine theta and y equals 3 minus 4 cos 2 theta, the question is express y in terms of x. Okay, so this is really interesting. Later in chapter 8, we're going to see that these are, in a sense, called parametric equations. So theta here is the parameter. X and y both expressed in terms of theta. So this traces out a curve of points x, y as theta varies. But again, this is not relevant for now, so we'll just forget about this now. But so let's solve the question. So we need to express y in terms of x. We're going to have to use the double angle formulas. We've got cos 2 theta, we know, is, well, we had three formulas: cos squared minus sine squared, 2 cos squared minus 1, and 1 minus 2 sine squared. Since our x is in terms of sine theta, it makes sense to use 1 minus 2 sine squared. So let's replace cos 2 theta with 1 minus 2 sine squared theta. So we've got 3 minus 4, that's minus 1, plus 8 sine squared theta. And note that sine theta is x over 3. So this is minus 1 plus 8 x over 3 squared, which is minus 1 plus 8x squared over 9. Done. That's y in terms of x. Okay, let's look at a different example. So the question this time is given cos x is 3/4 and x is between pi and 3 pi over 2. The question is find the exact value of firstly sine 2x and then secondly tan 2x. So sine 2x, well, we know, well, first so we know from what we did above, the double angle formula is 2 sine x cos x. So we need sine x. So let's just think about a triangle then. Here's x, cos is 3 over 4. So adjacent is 3, hypotenuse is 4. That makes the opposite side the root of 4 squared minus 3 squared, which is root 7. So we can see sine x, opposite over hypotenuse, is either plus or minus root 7 over 4. The difficulty is it a plus, is it a minus? Well, x is between pi and 3 pi by 2. Here's pi, here's 3 pi by 2. So x is in t. Because it's in this quadrant, sine is negative, so it's going to be minus root 7 over 4. Therefore, sine 2x is 2 sine x cos x, which is 2 times sine x minus root 7 over 4 times cos x, which we were given as 3/4. And this simplifies to minus 3 root 7 over 8. And then we'll do tan x, or tan 2x rather. So now tan x is sine x over cos x, which is, sorry, there's a mistake. It was not supposed to be 3 pi by 2, it was supposed to be 2 pi, which actually doesn't, because obviously cos would be negative if we were in t. So I'm sorry, in fact we're in C. We're in the C quadrant. x is between 0 and 2 pi. So sine is still negative between pi and 2 pi. 2 pi is over here. So we're in C. So tan is negative. So tan x is sine over cos, which is minus root 7 over 3. And therefore, we can now use the double angle formula. Tan 2x is 2 tan x over 1 minus tan squared x, which is minus 2 root 7 over 3 over 1 minus 7 over 9. And if we multiply top and bottom by 9, remember we want an exact answer, we're going to get minus 6 root 7 over 9 minus 7, which is minus 3 root 7. And that's the answer. So exact answer, you need to leave everything in terms of square roots. Your calculator might be able to give you the answer, but don't bank on it. But you shouldn't need it. You should be able to, as long as you're careful. And obviously you can use your calculator to do other bits of the multiplication if needed. But if you're asked for an exact answer, you must keep all of the square roots.